Okay, we're good there. All good there. Okay, excellent. All right, good morning. Welcome back to Foundations of Computing. I hope you all had a good break. Last time, excluding the advanced lecture, we talked about recursion and how to make functions essentially call themselves on the same instance of a problem, which is, to a certain extent, an algorithmic technique. But today, we will extend on that knowledge significantly, and we will talk about algorithms in general. This is one of my favorite topics. That's what I do in part in my research focus. You can think of algorithms as blueprints for solving problems in the most efficient way. And we'll look at two search algorithms. One will be linear search, and the other one is binary search. Then we will look a little bit into how to analyze algorithms. So how to understand whether they are efficient, whether they are good algorithms or not. And specifically how to measure their efficiency by looking at time and space complexity. And then after that, we'll explore a bit some, not all of them, some algorithm families. We will go through brute force methods, divide and conquer, a bit of dynamic programming, heuristic methods, and simulation algorithms. So at the end of this, we'll have a bit of a toolbox of blueprints for solving problems, hopefully. Excellent. So as usual, let's kick things off with some fun facts about Python. A couple of trivia. I left these more, I guess, lighter ones for the end. Python has its own philosophy of how you should code, and then that is included in some specific aphorisms and quotes which you can access by simply importing this, as on the slide, in your interpreter. Actually, let's do it. So if I go in my terminal and I import this, that's what happens. And so these are some of the principles, simple but powerful ideas of, beautiful is better than ugly and readability counts to guide your coding in Python to make your code more Pythonic, so to say. And then another one which I thought that was fun, which tells a lot about programmers, is that Guido van Rossum, who we already know is the creator of Python, who called himself in a funny way the benevolent dictator for life about Python, in 2018 retired. And after he spent 2 years in retirement, he declared that it was too boring, and so he came back on board on Microsoft as a distinguished engineer, where he's still coding in Python. Okay, so back to algorithms. What's exactly an algorithm? Now, you have had a very nice first lecture about this, with Shannon showing how you need to provide very precise instructions to a computer in order to make it do what you actually want it to do. And I remember that he had all this, scene along where he was showing off how if you're not precise enough and if you don't have a finite number of steps, it will become a bit of a disaster trying to have computer execute what you want to do. So an algorithm is a finite sequence of instructions that tells your computer how to solve a problem. Now, you can think of it as a recipe for cooking whatever, your favorite meal. And so you need to provide a clear step-by-step direction in every step on how to go from raw ingredients to the final cooked meal. Now, to be considered an algorithm, it has to have a few features, a few criteria. Well, first of all, an algorithm takes one or more inputs, just as a recipe requires ingredients. Then it must produce at least one output, again, our finished meal, if you want. Then every step must be precisely defined. Computers are not intelligent being, they're just a machine. They execute your instructions. So you can't just say cook until it looks good. The instructions have to be clear in how and when to stop to cook. Then finiteness, the algorithm has to end after a finite number of steps. No one wants a recipe that takes forever to finish. And then effectiveness, okay? So we should strive to have every step in our algorithm and the overall algorithm to be as simple as possible, but also as efficient as possible, both in terms of runtime and resources such as memory used. So we ask quite a bit of things here. Now, from the perspective of what is a good algorithm, there are three key criteria. I should say that definitely the first one should be given almost for granted. An algorithm must be correct. If it is not correct, it's worthless. In fact, if it is not correct, there's no point about talking about efficiency or readability, right? How fast is an algorithm that isn't correct? If it doesn't have to be correct, then I can make it arbitrarily fast. I don't need to run it anyway. Exactly. So, if you are designing an algorithm to, whatever, find the shortest path between two cities, better give you the correct answer. Second point, after correctness, is efficiency. Efficiency is very, very important in computer science. Also, from my perspective, is even more important because I do research in high-performance computing. So it's not enough for an algorithm to work. It has to work quickly, and it has to use memory wisely. If we take an hour to sort 100 numbers, well, that puts a limitation on what we can achieve with our programs and computers. So what we can achieve is actually dictated by how good your algorithms are, besides the limitations of the hardware. In other words, better be limited by the hardware, not by your algorithm. And then, of course, we have readability and maintainability. An algorithm has, and in general, your code has to be easy to read, understand, and modify. You write code probably once, but that code will be read many, many times. And you don't want a coworker, or most often yourself, come back 2 months later and do not understand anything of what was written, and you wanted to do maybe a minor modification. It takes more time to understand what the hell was going on in that code, rather than actually implementing the modification. Okay, so in terms of how do we evaluate algorithms, when we talk about an algorithm performance, we usually focus on two key metrics, at least at this stage. There are more metrics that will come in the years to come. The first one is time complexity. So what's time complexity? We measure here how long the algorithm takes to run based on the input size, okay? So it's like asking, again, taking again the analogy of our recipe, how does the cooking time change if I'm making dinner for 2 people as opposed to 20? Space complexity instead measures how much memory the algorithm uses. So if an algorithm needs to store a ton of extra data, probably that's not a good algorithm for dealing with large data sets, because maybe we don't have enough memory to store that data. And so you need to find an alternative there. So space complexity is very important when you are dealing with memory-intensive algorithms that take, or data structures that take quite a bit of space. Now, to describe time or space complexity, we use the big O notation, which gives us a mathematical way to describe how this algorithm scales both in time and space, or if you want, memory, as the input size increases. And we'll talk about big O notation next. Now, why do we want to analyze algorithms? But that's obvious. We will need, and you will need, in general, throughout your journey in computer science or in cognate areas, to be able to assess how efficient is an algorithm and to choose the tools that you have in your tool chain, right? So when to use one algorithm as opposed to another. So it's important to understand their features in terms of space and time complexity so you can do a good selection, and when you're writing a new algorithm so that you can understand how good that algorithm is. Maybe if compared to all other algorithms that it has significantly lower time complexity, that allows you to do things that were not possible before. Okay, so what's big O notation? So this gives us a way, again, to describe the efficiency of algorithms in terms of the input size. And it's a bit like a worst case scenario analysis. So it tells us in the end how the algorithm behaves when the input size gets very, very large. And here we have a few examples of time complexity. For example, and you might have seen this notation again sometimes, just a tiny bit in my previous slides. Order 1 means constant time, okay? So no matter of the input size, the algorithm takes the same amount of time to run. Okay, so if I increase the input size, I still get the same amount of time. And we have seen an example of this, which is indexing in lists or tuples or strings. Okay, we also in the advanced lecture discussed a bit why is it that it takes every time just constant time to access a specific element in a list, even if the list grows. Linear time, the time that it takes for the algorithm to run, grows proportionally to the input size. And so this is like reading or searching, which we call the lookup as well, through for a particular value through the elements of a list. What we have to do is to loop through potentially all the elements in the list to see which one matches, and therefore, as the list grows, the search time grows proportionally. Then Next one, quadratic time. Okay, so all this quadratic time, cubic time, quartic time, quintic time, typically are associated with loops. The more loops you nest, so let's say, for example, I'm looking through different lists. Each list has n elements, and then I start nesting loops. If I nest 2 loops, obviously for each element of the first list, I am also looking through all the elements in the second list, right? And overall, since I need to look through all the elements of the first list, I will get quadratic runtime. So order n squared complexity. If I nest 3 loops, order n cubed, etc. Of course, this is assuming that I'm looking through the elements of all the lists, and each list has order n elements in there. Quadratic time, traditionally, I would say, for most of the algorithms you'll be looking at in computer science is already quite bad. I mean, ideally, you would like to have lower than that. But there are obviously algorithms that behave much worse than that, and typically harder problems. Then logarithmic time. This is an interesting one. It's the first one. It's a bit of more of a funny function here. And so the idea here is that your algorithm gets more and more efficient because your input size gets reduced, your effective input size, so let's say that way, gets reduced at each step. And so an example of this is binary search, and which we'll cover directly in this lecture. Okay, so BigO help us compare algorithms in a worst case scenario. I talked about time here. BigO notation is applied in a very similar way to space complexity, so memory. And here we have a bunch of curves. So let's say if I ask you which one of those complexities is the top curve. Simple question. Yep. N squared. N squared. Okay. What's the one below? Correct. So we got n squared. Look how big is the gap between n squared and also the next one, okay, in terms of runtime. I plotted this to give you an idea of how much things change when we move across these different scaling. So the next one is linearithmic, so it's n log n. And then the green one will be, it looks already very linear. It's order n. And then we have 2 there, and you see that they almost overlap. And it turns out that the one at the bottom is order 1, and the black one, it's, oops, what did I do? It's log n. Okay? So things change enormously when you have different scalings. So if you're trying to process millions of elements, so you have an order n squared scaling, you will see it. Your computer will take time to process those elements. So in general, you would like to, ideally, of course, you would like to have an algorithm that has constant time all the time. That's not possible, but in general, staying between order n and log n, maximum n log n is where you want to be. Not always possible, absolutely, by any means. Okay, so let's start with the first example. We look at two searching algorithms first before we go a bit into all the other families. So what we want to do here is a very simple example. We pretty much have covered this already. It's just to warm us up. It's linear search. What we need to do is to find the position within a list of a particular element that matches a value, okay? And here there is some Python code that achieves that. We have this search function. We have the value that we want to match. We give it as a parameter numbers, which is a list of numbers, as you can see there in the examples here. And after that, as we know, typically for lists, what we have to do is to loop over all the elements in the list until we match that particular value, which we implement here with this loop, for loop. And if we find that value in our list, then we return the associated index in the array. I don't think I have to demonstrate this, otherwise we return none if we haven't found the value. I don't think I have to implement this. It's simple enough at this stage. And obviously here, the time complexity is order n. And we'll go a little bit more in detail on this. This is a bit of a visualization because it's good to keep this in mind because we'll do binary search later. So that's the simplest visualization that we have. You know, you have a bunch of numbers, you step through that, and then at some point, if you match the number, you found it, you return the index of that list. Now, to get us used to do a tiny bit of algorithm analysis, let's go through the features that we discussed earlier. First, correctness. So is this algorithm correct? Does it give us the right answer every time? And the answer is yes, okay? So the algorithm checks every element in the list. So if the value exists in the list, it will find it. Efficiency. Okay, now let's get us used at thinking about how do we compute a bit in our brains this time complexity. Let's look at the best case scenario. We're looking for an element in the list and, for a value and a matching element in the list. Best case scenario, the very first element, we start looping at from the first element of the list until the last. Best case scenario, we find that value at the first element. If the list grows and that element stays there, the algorithm is not going to take more time as the list grows, right? This is always going to access the first element and find that value. So that would be order 1 or constant time. Worst case scenario, the opposite. It's always the last element in the list. And as we keep putting elements in the list and we keep that as the last, it's going to take exactly order and time. On average, statistically, your value, if the elements are randomly organized, if the values in the list are randomly organized, is going to take the average between the two. The average is still order n. If you want order n half, we don't put that 1/2 in there. It's irrelevant because it's just an order, a worst case scenario argument. So space complexity, order 1, I just need to keep track of the index of the elements and then store the value once I found it. Right, so limitations, obvious, inefficient for large data sets, potentially, time consuming, we're searching frequently, can we do better? Now, the answer is we can, but the issue is that there's a caveat, and we can do better if the list is sorted, okay? So if the list is sorted by increasing values, for example, we can do better. And we can do better with an algorithm called the binary search. So, and this is quite clear. We have a prerequisite, an assumption. You know, if that is not true, this algorithm will give you potentially garbage. We cannot guarantee correctness in that case. So if the list is sorted, then what do we do? Okay, we can think of getting our value, and given a list of size n, we can compare that value to an element in the middle of the list. Now the list is sorted. Obviously, if the value of that middle element equals our target value, we return the index. We're done. But if the target is smaller, okay, than our interest value, we can repeat the search. If the target value, which is our interest value, is smaller than the middle value, we can repeat the search, but we don't need to look at the elements in the right half because they're going to be all bigger than the middle element because bigger or equal to that middle element, right? So I need to look only in the left list. Vice versa, if the value I'm interested in is greater than the value of the middle element, I don't need to look at the left list. Those values are going to be all smaller than the middle, smaller or equal to the middle element. I need to look only at the right list. Now, I can repeat this process in the very same way until I find my element. And this, we'll see, leads to a time complexity of order log n, which is much better, you've seen the graph, of order n. So how do we do this? So in this version, we use an iterative approach to binary search. You can implement a binary search also using recursion. But that's a classical example of binary search here. So what we do is have this function. Once again, our value of interest, numbers, is a list with our numbers in there. And we are interested in looking at value. We assume the numbers is sorted, okay? Then what we do is to define two indices. We call them left and right. And at the beginning, I'm looking at the whole list. So left is going to be the first element, or the index of the first element, so 0. And right is going to be the last one. So it's n minus 1, or the length of the list minus 1. Then we say we start looping, and we loop until left is less or equal to right. What does that mean? Well, there are still elements in the portion of the list that I am looking, okay? Because if the two at some point overlap, then I'm done. There's no other elements to search through. And as long as that condition is met, we can define what's the middle element between the left and right. And that's simply defined in this case, the different definitions, or maybe just a couple probably, but we define it as left plus right integer division 2. Okay, so if my indices were going between 0 and 4, that will be 4 plus 0 divided by 2, which is 2, which is the third element. The list has 5 elements, is actually the middle one. And if the indices were going from 0 to 3 instead, there will be 1, which will be the second element. Okay, 3 divided by 2, integer division is 1. Okay, so we define the middle element. If the value equals, as we said before, that the value of that at that index and the index of the middle element, then we return that value. So we return the index, sorry. Then if the value of the element position at mid, so numbers index at mid, so the middle element in the list is less than the value of interest, then what we do is to move where left is. Why? Because the value is greater than the value at the middle element in the list, so I don't have to look again at all the left portion of the list. So what I'm going to do is to move my index for left to mid plus 1. I already looked at mid. It wasn't the right value, so I start from the next one. So basically, I have now halved the list that I have to look at. So I have a sub-list which is half of the size of the full list. And vice versa, of course, in case we had the value smaller than the value at the middle element. Now you see we have a while loop here. So we repeat this until we find our element. If we don't find it, if we find it, we return the index. If we don't find it, we return none. But the idea here is that every time that I run one of these iterations in my while loop, the number of elements that I am searching through is halving. Okay, so I'm not doing order n work because every iteration I'm looking at half of the elements. I can do this only and only because they are sorted. And so here there is a bit of a visual illustration of what's going on compared to our very simple case earlier. So in step 1, we're looking for target here, which is 6. So whatever element in this list has a value of 6. And initially in the first step, left is 0, as I said before, right is 6. And we compare to the middle element, which in this case is element number with index 3, which is the 4th element in the list. Compare it, it's not 6, so what we do, but 6 is greater than 4, than the value at middle. So I need to move left, not right. So left now is moved to be 4, which is the index of middle, 3 plus 1. And then I do exactly the same thing. Now my list starts at index 4 and ends at index 6. And there's only 3 elements in there. I did just 2 steps here. I look at the middle element, and that turns out to be 6, as a value of 6. So I found my element, and I can return the index associated with that. Okay, so algorithm analysis, correctness. As long as the list is sorted, the algorithm is correct. It guarantees to find your element if it is in the list. Okay? Efficiency. Okay, so best case scenario, same as before, except, same for linear search, I mean, except that now I am assuming that the element is the one in the middle of the list, right? So if I am looking for that element and it happens to be all the time the mid element in the list, first step, if I grow the list and that element is still there, it doesn't take more time to run to find that value. So it's order 1, it's constant time. Worst case, Well, the value is not present, or it's a one of the two ends. Now, what I'm doing is having each time the list that I need to search through, and this process can be proven, and you can try to do that to be order log n. And that's basically what you should report as the asymptotic or big O complexity of binary search. Oh, in terms of space complexity, I had an interesting comment here. The iterative version uses order 1 extra space. It's not actually 1, it's more because you have to keep track of the indices. But it's still a constant number of indices. It doesn't grow, the number of indices that I need to keep track of as I grow the list size. But the recursive version instead does, and it uses order log n space because I have to allocate a call stack of order log n. And you can imagine that if you do the recursive search, basically every time the function calls itself, and in the worst case scenario, it's going to call itself order log n times. And that will cause to have associated number resources proportional to the number of calls. Okay, excellent. Now let's start looking more in general. So I gave you two examples. Actually, binary search falls in the category of one of these larger families. It's a divide and conquer approach. But here we have not all of them. There are many classifications of algorithms that are possible. This is an initial one, and this is a very simple one. I'm trying just to give you an idea what kind of algorithms there are out there. So looking at the big picture, 5 families here. The first one is brute force methods. Okay, what do we do here? In brute force methods, we look at all the possible solutions until we find the right one. Right. Simple, but obviously, if your solution space is too large, infeasible. Divide and conquer. So in divide and conquer, we take our problem and use a strategy of dividing the problem into sub-problems, and we solve each one at a time, and then we have to find a way to recombine the solutions of all the smaller problems, and from those obtain the solution to the original larger problem. Dynamic programming. Okay, typically here you would see in dynamic programming the use of recursive algorithms and then storing intermediate results. But the main idea about dynamic programming, I'll come back to it later, is that you still have, you still break your bigger problem into sub-problems, okay? But these sub-problems are overlapping. And so since they are overlapping, you can store the solution of the overlapping problem and reuse it. And this will be more clear soon once we look at an example of this. Heuristic search instead is when you give up the exact solution because maybe it's not possible to find the exact solution in a reasonable amount of time. And so I am happy with a solution that maybe is not optimal, maybe it is, but maybe it is not optimal. I don't have a guarantee about it, but it's good enough. Okay? And the advantage is obviously that heuristic must be significantly cheaper than brute force. Otherwise, it defeats the purpose of doing this, of giving up one of the most important constraints, which is correctness. Well, it's actually not correctness, it's exactness of the final value. It still needs to be correct as an algorithm. It needs to do what it's supposed to do. So, third one, simulations. This is a huge family of algorithms. And in fact, I work in that area pretty much. And these are algorithms that there are so many, but the main unifying idea is that they simulate real-world processes. And these real-world processes are very complicated. So complicated that sometimes you can't even do physical experiments to test whether your hypothesis is true or not. It might be too expensive, it might be too slow, or it might be that simply there are no ways of doing it. And so you end up simulating these processes using a variety of algorithms, and the specific algorithm will depend on the process that you use. And it could be using random data if you use statistical techniques, or it could be using what is called here synthetic data, which means that you use data that it's produced not necessarily from a physical experiment, but from a digital experiment. Okay, so your inputs, you decide the inputs, and you take the responsibility of saying that those inputs are correct. I don't particularly agree completely with this definition of synthetic data. This is a very high-level thing anyway. There are many simulation algorithms that actually use real-world data as input. Another classification here is, so if we take those families, still we can classify them in an orthogonal, from an orthogonal perspective, which is that we can take our algorithms and classify them in exact and approximate methods, okay? Which is different from correct. So exact methods, I guess, again, provide a guaranteed correct solution means that provide an exact solution to that problem, okay? Your algorithm needs to be running and doing always what's intended, okay? So that's algorithm correctness, but the solution of some algorithms might not be identified as the optimal or best solution or exact solution to that particular problem, okay? So let's think of it, for example, to make an example. I want my algorithm to solve an equation. And to solve that equations, there are two approaches. One is the analytical approach, right? I actually solve the equation and give a solution which might be 2, the number 2, or pi, for example. Another approach is to use an approximate method that discretizes my equation, okay, and uses numerical approaches to trying to get as close as possible to that solution, but is not exact. It's not exactly 2. It might be 1.99999, but it's not 2. So it's very close, it's approximate, but it's not the exact solution. Still, the algorithm is correct because it's doing what it's intended to do, okay? So example of approximate methods is heuristic search. As we said, simulations are approximate typically, okay? Although you might argue that some simulations, if you increase runtime and increase the computational demands, might get so close to the exact solution that you couldn't numerically tell apart whether it's exact or not. And there are many cases of this kind. While exact methods, as we said before, brute force by definition, we look at all the solutions and we're trying to find one. Divide and conquer, then dynamic programming are typically exact. Obviously, when to use which? Obviously, if I have an algorithm that is exact and runs in a reasonable amount of time, I want to use the exact approach. That's the answer, really, to that question. Okay, so let's start looking at a couple of these. I'll go through these and then give you just a 5-minute break. So the first one is brute force methods. I want to go through these I will go through these relatively fast because it's a simple concept. So we try every possible solution, and once we tried all the solutions, we just select the best one. Advantages, simple to implement, obviously, and guarantees to find the optimal solution, if there is one. Very inefficient, typically, okay? Very, very inefficient. Not that smart. But yet, sometimes, that's the only thing that you can do. A very simple example. Checking whether a number is a prime number. So what we do here in this function is prime, is to check whether we have a prime number, a number which is divisible by only by itself and 1. Okay, that's the definition. And we provided this number, which we don't know whether it's prime or not. If the number is less or equal to 1, we return false because a number 0 and 1 are not prime numbers, okay? And then, if it is neither 0 or 1, what we do is to simply loop through all the numbers until that number minus 1. Minus 1 because range is exclusive. So from 2 to n minus 1. And we check using modulo operation if that number is divisible by I. So if it is, we return false at the first occurrence, right? Otherwise, we return true. Well, obviously, this will do, but you can imagine that if I start having very large prime numbers, what I have to do, worst case scenario, is to check, well, by definition, all the numbers until n minus 1 to find out that is actually a prime number, which is quite horrible. So it's very inefficient for large n. But it will do for small prime numbers. Okay, so a few minutes of break, then we come back and we analyze the remaining families of algorithms with a few examples then. All right, so the next algorithm family is that of divide and conquer approaches, which is a very interesting one. So in this case, what we do is to break the problem into smaller, independent, very important word, subproblems. Solve each one of those subproblems and then recombine the result somehow. That's the high-level idea. How you implement it, it's different case by case. A very good example of this, famous example, is merge sort, which we'll go through right now. And one we have seen is binary search. Why do we do this? Well, we hope, and better be true, that by doing this, we reduce the time complexity of our final algorithm, okay? There might be other reasons that will come in later years, so which I will tell just a sentence about it. One of those is parallelizability of your algorithms. These days, it would be incredibly wasteful and inefficient to run, in the end, production code if it is performance determining by running it on a single core, so by doing a sequential algorithm. In reality, we have multiple cores that operate in parallel on your CPU and in general on other pieces of hardware. And of course, divide and conquer is interesting because it exposes that parallelism. But that's not the case for today. The idea is that if we do this, we have to find a way to reduce the complexity. Yes? That's correct, yes. In fact, it sometimes it can come actually at the cost of space complexity. But we're very interested typically, in this case, in time complexity. It's not always the case, right? I can imagine there would be approaches where you're trying to perhaps reduce the other one, but it doesn't come really too much on top of my head. Typically ends up reducing time complexity and potentially increasing space complexity, because you have to keep track of all these sub-problems at the same time. Okay, so let's look at merge sort. That's a very, very, very nice algorithm, classic, sorting a list. So sorting a list, if you try to sort a list by brute force, what you would do is to compare pairwise all the elements and form the sorted list. Okay, it's not a very difficult algorithm. I'm not going to explain it. You can find it out or do it yourself, probably. But the point is, because of the pairwise comparisons, is order n squared. Okay? Now, the idea here instead is that we have two stages. The first one is the divide stage, where we recursively split a list into two halves until the sub-lists contain only one element. Why? Because I know how to sort one element. It's already sorted. Then, once I've done this, I need to figure out a way to smartly recombine all the sub-lists into a full sorted list. And that is the conquer, or also actually called in this case, merge phase, where you have to find a way to combine two sorted halves into one sorted list. But the key point is the two halves are sorted. They are no more randomly ordered. The two halves are sorted, and that's the key principle that we are going to use. Okay, so in terms of just putting it more formally, so we take a list, recursively divide the list until each sub-list contains one element. Then we merge each pair of sub-lists, comparing those elements, so that I can obtain at every step of the merge sorted sublists, and I keep merging up. Okay, how do we do this? Now, we'll spend a bit of time on this because it's an interesting algorithm and there's some elegance and complexity into it. So we define here, there are multiple ways of doing this. The one we take here is a recursive call. So we're using recursion here. So we have this function, merge sort, list is our list that we want to sort. If the length of the list is less or equal to 1, we return the list. Right? We're done. We know how to sort one element. Then we have to split the lists. Right? If it is not true, I have a list which is longer than 1, I have to split them. And I keep doing that until I get to the case where there is only one element. And the way I do this is a slightly different way from binary search, but pretty much almost equivalent. Here, we don't keep track of left or right. We just say, take the length of the list and do an integer division by 2. Okay, that's fine. Just a reference point, essentially, to find that midpoint. Once we have that midpoint, what do we do? Well, we define the left half sublist and the right half sublist. And the left half sublist is defined as the returned value, so the output of, again, merge sort on a list now, which is the left sublist. So I go from element 0 to element with index mid -1, because that's not inclusive, and call, again, recursively merge sort on it. And they do the same for the right list, okay? So obviously, what's going to happen there? So this is going to call itself multiple times. So one of the first things that happens is that we keep dividing recursively these sublists until the sublists do not contain, until the sublists contain only one element. Okay? Now I haven't found yet a way to merge these back. Okay, so I'm dividing, keep dividing. That's very nice. At some point, I will reach a point where I hit that if length is less or equal to 1 and return the list with one element, which is sorted according to the definition of sorting. Now I need to deal with the merge. So how do I merge back? So, you know, at some point, I look at this tree, I have my big list, I keep splitting, and then I can imagine having all these sublists which are very small. How do I take those sublists and recursively merge them back while sorting them? With the requirement that each of the sublists that I keep merging stays sorted. Well, I do it through this merge function. What's this merge function going to do? Well, it takes two sublists, left and right, and we want it to return a merged list which is sorted. So we define I and j here. And what are these I and j? These are indices. I is an index in the left sublist, which I can iterate through, right? So I want to iterate through the left sublist. I is my index. And then I have my right sublist, and j is the associated index. Then I run this iterative approach, where if I is less than the length of left, so what that means is that I still got elements that I haven't looked at in my left sublist, and also j is less than length of right, which means I still got some elements in the right sublist that I haven't looked at. Okay? So we are iterating through the two. For each I and j here, I compare whether the element of the left list, the ith element of the left list, is less than the jth element of the right list. If it is, I take my sorted list and append the element in the left list. Why? Because it's less than the right list. So I am sorting here. That's what this is doing, right? So I am figuring out how to compare the elements. The two lists the two sublists are sorted, okay? So every time, all I need to do is to take one element from the left list and start comparing it to whatever element I happen to be at this point in the right list, and take the one which is the smallest of the two and append it to my sorted list. In the opposite case, of course, I append right. What it means is that right is smaller. The element in the right, the jth element in the right list is smaller than the ith element in the left list. Now, as I do that, once I finish that loop, there may be cases where I ran out of elements in left or elements in right. And so I still got some elements in one of those two sublists that I need to append. But those have been guaranteed, one, to be sorted, and 2 to be larger than the elements that I already have in the sorted list. So I just extend my list and put those elements in. That's what's happening here. We'll go through this more in detail because it's a bit difficult to understand. So that's the full visualization. So let's say we have this specific list here, 529, 156. We want to sort it. This thing which is very annoying. Don't know how to get rid of it. And the output should be this one. So we are doing exactly the case. We take our list, and we have in green the divide, green whitish, the divide stages, and then we have in, what the color is, violet, bluish, the merge stage. So as I said before, we use the recursive calls, and we get to the stage where we split first in 2, then we keep splitting until we reach sublists which have only one element. The first one that's going to hit that category is this 5.2 over here. This 5.2 over here. And what do? Well, in that case, when I call the merge function, I have only 2 elements. So I'm going to do is to compare 5 with 2. I know that 2 is less than 5, so 2 comes first and 5 comes next. Then another interesting case is I need to take 2, 5 and now merge that with 9. And so what do? Well, I have to take 2 first and compare it to 9. That's less than 9, so that goes in. 5 with 9, less than 9, that goes in. And then I'm left with only the right list and extend. Okay? And that's very similar to the other one. So the really interesting case comes then when I have 259 and 156. So what do here? Well, we do the following. So we have the left list. Again, we reach that point, the final merge. And the right list. That's the algorithm that we have in merge, but that's what's actually happening here. So we compare the first element of both sublists. These are merged, right? That's the key principle. So 2 is less than 1, we append 1. Then now, 1 is gone because our J index has moved to 5. Right? So we are not going to care anymore about that 1. So again, 2 has left there, so the ith index of left is there. So we compare 2 with 5. Which one is smaller? Is 2 that goes in. Okay? Now we can move the I index in the left list to 5. Okay? So we have J, so both J and I now are 1. We compare 5 with 5. It doesn't really matter at that point which one goes in. One of the 2 goes in. We proceed. In this case, the one that went in was the right list. So we have I, which is 1, and J, which is 2. Okay? Compare 5 with 6, and append 5, and so on and so forth. Okay? So what's the key take here? If I have n elements, let's say n over 2 elements in the left list, and n over 2 elements in the right list, how much time do I take to do this merge?
As you're building it, right? Like, for example, there we have 9 versus 6,
Mm-hmm.
and you're appending 6. you need to look through the list to figure out where the 6 is supposed to go because you're inserting it into the list. You know it's sorted, or like that list that you're building is sorted, but you have to figure out where to actually insert it.
Do you? Because J and I move pretty automatically. I don't have to figure it out. I know where it is.
So it always goes on the end.
It always goes on the last element that I compared. Right? I and J, that's the point. It always goes on the last element that I compared. So let's try to understand. So squared, where will it be coming the square? The square comes, as you say, as you mentioned, as your colleague mentioned, if I take each element of the left list and compare it to each element of the right list. Why? Because I have n half or order n elements in the left list, order n in the right list. If I compare pairwise, I get order n squared. Is it what I'm doing here? Well, let's again look at this. How many elements are compared with each element of the left list?
So basically you're saying because the sublists are already sorted, you can just append to the end, and therefore once you get to this stage, it's effectively linear, right?
Correct. So what is happening here is because the list is sorted, I don't need to look through all the elements. For a given element in the left list, I don't need to look through all the elements in the right list. I need to look only for a constant number of elements in the right list. Okay, because the list is already sorted. So we have to make only one comparison, well, a couple of comparisons. But the idea is, again, that because of the sorting, we got rid of the fact that I don't know whether, so let's say if I have to, I can look at one in the, so I have 2 in the left list, I can look at 1 in the right list. I know already that 2 is greater than 1, so 1 goes in. But then when I look at 5, okay, I know that 5 is greater than 2, and 2 goes in. I don't need to look at the remaining elements of the right list because there is no chance that after 5 there is going to be another element which is less than 2 because the list is sorted. So this means that I do order 1 work for each element of the left list and the right list, and overall each list is order n, so I do overall order n work. Okay? And that's very interesting. Now, that's not the end of the story, but that's interesting. So let's go back and see how do we get to this final scaling here. Oh, by the way, another word for how an algorithm, the time complexity, is also how the algorithm scales with respect to the input size, that we're talking exactly of the same thing. In this case, how the time complexity, the time scales with input size. Okay, so we know that this merge takes order and time. But that's not the end of it, because we still have to deal with multiple stages of the merge. How many stages? Log n. Because I have to take that list. Every time I take the full list, I start building sublists, which are half of the size of the previous stage. For each one of the reassembling stages of the merge, I do order n work, but I have log n stages. So the overall time complexity of merge sort is order n log n. Again, this is not very formal, it's just trying to make you understand, and you will do this in foundations of algorithms properly, hopefully. So here is an example. If I have an input of size 8, that's where the logo comes in. You can see it here. I recursively split every time by 2. And so I have 3 splits. So 3 stages of split. Okay? Log 2 of 8 is 3. Or in other words, I divide 8 by 2. which is 4. I divide it by 2, which is 2. And I divide 2 by 2, which is 1. 3 stages. And then at each one of those stages, I need to merge back. And to merge back, all the pieces that I have are order n, by definition. And so I do order n work. And with each one of the merge doing work which is proportional to the size of the two sublists that is dealing with. Excellent. So final slide on this, divide and conquer. That's a big achievement. It's a very cool algorithm. Order n log n as opposed to order n squared. Not much of an assumption here. Our initial list is not pre-sorted. Space complexity. Well, there you go. Well, to some extent, we have to deal with the fact that at every stage we have to have this order n storage because obviously we need to store all the, we need to keep track of all the sublists. Yes?
So this is super fast, like it's even theoretically faster than other fast sorting algorithms because it's willing to take that penalty in memory. Is that a good summary? Because I feel like there's other sorting algorithms which people do use instead of merge sort. I'm like, why would you ever use that if this is so fast? Is it because of the memory?
Yeah, so for example, if you want to do in-place sort, that you don't have to have the extra buffers for the merge sort, right? And but then you might want to be happy probably with quadratic.
Can you take it to the more extreme? Like, is it possible to have a general sorting algorithm for this random list that would be faster than merge sort if you were willing to have even more space complexity, or is this like the fastest that you can get?
That's, at the moment, that's the fastest way that we know.
This one?
Yes.
So there's you can't sacrifice more memory to get it any faster than this?
No. Not that we know. Maybe some one of us will discover it at some point, but not that we know. Okay. Next. Dynamic programming. So that comes after merge sort intentionally because people get confused about this. So here we have, again, an approach where we divide our bigger problem into smaller subproblems, but each subproblem is solved only once, and we store the solution of this to avoid recalculating it. Now, the key point is that these subproblems are overlapping. In divide and conquer, they are not overlapping. Okay? The only reason why it makes sense to store the solution is because they are overlapping. If they weren't overlapping, then it wouldn't make any sense to store that solution. And I will show you an example of this, which we already pretty much have seen. Fibonacci. Remember our Fibonacci function? I said at some point, this recursive Fibonacci is not great because it gets quite expensive. So in case of the Fibonacci function here, what we are doing is we want to compute the Fibonacci numbers. We know that to get the nth Fibonacci number, we have to sum two previous Fibonacci numbers, okay? And so we have a recursive implementation here, and the recursive implementation says, as we have seen before, there are two base cases. If n is 0, return 0. If n is 1, return 1. That's the definition of the Fibonacci numbers. And then we have a recursive case. The recursive case is calling the sum of the Fibonacci number n minus 1 plus n minus 2. Okay, cool. Now, what's happening here? This is happening. Okay, so this is a picture for F5. Now, if we call F5, F5 is going to call F4 and F3, okay? F4, in its own turn, is going to call F3 and F2. But F3, in its own turn, when that will be executed, it will have to call F2 as well, again, and then F1. F1 is a base case, so that's fine. But F2 will be recomputed. So F4 and F3 at the moment are computing again from scratch F2. Okay, so we have 2 times F2 here. Then F4 itself is going to call F3, which was computed potentially before, or it has to be computed depending on how the call stack goes here. And so we have 2 calculations of F3. Then F3 again calls F2. So we have 3 times calculated F2 here, okay? And then we hit the base cases. So what I'm saying here is that there are many instances where we are recomputing exactly the same thing. And that's not fun, because if you have very high values of Fibonacci, there is an explosion of cases where there are these overlapping cases. And if they are far up high, then you need to go up to, well, all down to the recursion tree. So this results in an order 2 to the power of n number of recursive calls, which is highly undesirable. Obviously, that's a scary scaling, but for small Fibonacci numbers, that's fine. But for large Fibonacci numbers, it's definitely not fine. Okay, so what's the solution here with dynamic programming? Dynamic programming has 2 techniques. One is called memoization, and another one is called tabularization. We just go through memoization. Here, what you do is to store the results that you calculate as you go. And then, once it happens later on in the calculation, in the recursive stack of calls, that I am calling again that case, I'm not going to compute it. I just look it up because I have stored it. Okay? And so the recursive call with this memoization technique form the backbone of a dynamic programming approach to Fibonacci, for example, that reuses the solutions as we go. And here is an implementation, again, very simple. We have a dictionary. This time, the only difference is that we keep this dictionary called FibMemo. And every time that we compute a new Fibonacci number, we store it in FibMemo. Okay? So base cases, if n is not in FibMemo, which means that we haven't done that Fn, Fibonacci of order n, we calculate it, okay, using recursive calls, but as soon as the number is calculated, we store it. So how does this work? That's the version with dynamic programming. So I have F5 again. Now imagine that every time that I call Fibonacci, I have 2 calls, Fn minus 1 and Fm minus 2. And F minus n minus 1 in this case goes first. So F5 calls F4. F4 calls F3, which calls F2, and F1, which calls F1, F0. So I cannot resolve anything until I hit F2, which hits the 2 base cases. I have the 2 base cases, and I get F2. F2 gets stored in the dictionary. Now I take F2 and F1 and with that, I obtain F3. F3 gets stored in the dictionary. Now I hit F4 as I'm going back up in the call stack, right? And I call F3 and F2. F3 is stored. F2 is stored in this case, and F3 has just been calculated and stored. So I don't need to recalculate F2 here. And then I go up again to F5. F4 gets calculated with F3 and F2. I store F4, but I have also stored F3, and I go up and do F5. Now you can see that I'm not growing all the, in this case, for you, right side of the tree. So this solution grows up linearly. Okay, so that's a big deal because we have reduced, and I don't know why I don't have it here, but we have reduced the number of occurs from order 2 to the n, which we hit in a very, typically properly for a very large n, but that's the point of complexity is Obigo notation is an asymptotic complexity to order n. And here just to disambiguate on dynamic programming, once again, to say it multiple times, what the main difference is that in dynamic programming, the problems are overlapping. If I didn't have these overlaps, F3, F2, F3, F2, there would have been no point in doing this. Okay? Okay, last two families. Simulation. Okay, as I said earlier, simulations algorithms are useful when you want to model a process which is typically too complex to do it directly, right? For example, actually in the real world. I don't know, a chemical reaction might be too complicated or whatever. Something very complex. The financial market behavior. You know, how do you actually do the experiment? So what we do is to have a model, and that model might be high fidelity or low fidelity, depends how complex is the model that you manage to build. Typically, the more complex the model, the more complex the algorithm, the more computational cost in it. And with those models, you simulate, and if you want, you predict what happens. So it's going ahead in time and saying, I don't know, if for example, what I do is like taking the structure of a drug and putting it in our cells and see whether it actually obtains the therapeutic effect which is desired. And this is all simulated, okay? So I'm predicting that process. And you can do this for a number of different applications. Actually, the applications are becoming enormous. You can use also AI for simulations. So some cases here, weather forecasting. How do you get your weather forecasting? Well, you get it through simulations. What we do is to take the current state, or actually plus a ton of historical data about the weather, and there are various models of how the weather behaves. Most of them so far have been physics-based, but most recent ones use AI to propagate the behavior of the weather in time. And we use a big supercomputer to do that with millions of cores. And that turns out that is, you know, if you want accelerating time and looking up what happens with the weather. Very similarly, planetary motion, astrophysics uses a lot this kind of algorithms. Modeling biological and chemical processes, this is a huge area. So there's so many things in that, from drug discovery to discovering new proteins, bioinformatics, discovering new materials with specific properties that do not normally happen to be in nature. And then another big one is financial market prediction. And in general, strategies for trading. For example, you might have heard these days of algorithmic trading. That's designing algorithms that automatically trade stocks based on different strategies. Or in general, there are other algorithms that solve the Black-Scholes equation for predicting the price of a stock or an option. The details of these are very specific to the application. A very simple and common simulation, which is always brought up, is that on Monte Carlo simulation, so this is kind of a statistic simulation, which works when you're dealing with probabilities. So it works to some extent in finance and also in science, depending on the kind of problem that you're tackling. So the idea here is that we use random numbers to simulate a process, which doesn't seem very meaningful when you say it. We are not simulating randomness per se, we are using randomness to simulate a process. And the idea is that we rely on a very important statistical law called the law of large numbers. What this law says is that as you increase the number of trials of a stochastic process, okay, you will reach at some point for a very large number of trials the true expectation value, which is, let's say, you can think of it in simple terms as the average. For example, I take a coin, heads or tails. If I repeat the process sufficiently long, I will reach a point where I know that the probability of heads is 1/2 and the probability of tail is 1/2. Okay? I can figure it out without Monte Carlo simulations, but I can actually simulate it. And what this principle is saying is if you do enough trials, you will get 1/2 as a probability of heads and 1/2 as a probability of tails. Okay? So it's obviously very useful for problems that involve a certain degree of uncertainty and widely used in gambling games, financials, and actually also very complex scientific models, typically physics and chemistry. Okay, so a simple example here. I have a gambling game where you roll 2 dice. You take the sum of the results from the 2 dice. If the result is between 8 and 11, you win $2. If the result is 12, you win $6. In all other cases, you win -$1, so you lose $1. Okay? And you can simulate by using Monte Carlo and random numbers whether this is worth playing or not. How do you do it? Well, you can figure it out with very simple maths without doing Monte Carlo here. Okay, so you can calculate the expectation value of this game. For those who are maybe in the realm of finances and stuff, or doing mathematics and statistics, that's a trivial task. But we can simulate it. We import a random here, and then we have a function that rolls our dice. And what this random.randint16 is doing is randomly choosing a number between 1 and 6, which is 1 dice. So we sum the value of the 2 and return that. That's the value that we get from our game. Then we have this function where what we're going to do is to run a certain number of trials. Okay? And this number of trials, we want it to be large, typically. The larger it is, the closer that gets to the value that we will get at the end. To the actual expected value of the winnings. Okay? And so here we loop over the trials. We don't really need to store the value in range because we are using this just to repeat the process n times. And if the result is between 8 and 11, we return +2. If the result is 12, we return +6. And if it is neither of those two, we return a -1. And then with that, we can estimate returning the winnings. Whether the game is worth playing or not is actually better here. Return the winnings divided by the number of trials, because that tells us on average, okay, what's the average winning or loss as I play one of these games. And obviously, if the average or the expected value of the number is positive, I am winning, so it's worth playing. If it is negative or 0, it's not worth playing, because I'm either, it's not doing anything, I'm wasting my time, or I'm losing money. And so I think I had a very quick example of this somewhere, which is this function here, so that we have coded up exactly as it was in there. But what I've done here is also to code up a very simple function to, instead of doing thousands of trials, to do it exactly, okay, so without the simulation. And so I created this function called the profit, which does exactly what we said, right? So it returns a 2 if the number is between 8 and 11, 12 if it is 6, and in other cases it returns a 1. And then I just calculated the expected value. So what I did here is to create a list where I run over all my possibilities, right, at each time. So I go range 1 to 7 because 7 is exclusive, so it will give me numbers between 1 and 6. And I do in a double loop, and I sum the two numbers. Now, obviously, I want to apply the profit function to these numbers, so I can use map here. Okay, so I can return the actual profit that I make. And I do it for all possibilities, which is just 36. And then I take the sum of these numbers, this profit that I made, and I divide it by 36. And that gives me the expectation value for each one of those trials. Then what I did here is to use the original function that simulates the trials, okay? And I took the total winning and divided by the number of trials. These two, the exact one and the Monte Carlo one, should give values. Well, the exact one will give always one value, which is the correct one, but the simulation will get closer and closer to the exact one by the law of the larger numbers as we do more and more trials. So let's see, for example, I might run this from the terminal. It's always safer. What's happening here? Oh, maybe if I run it directly from here. That's okay. So it wasn't importing math. That's okay. Okay, so we have the result here. And so you see that after forget the total winnings, this is actually the average winning, okay? So I should put here average winning. So the average winning after 10,000 games is $0.355 per game, while the correct number is 0.361. Okay, that number will keep changing. So as you can see here, is slightly different from the one previously because we are using randomness. Okay, so that's the principle of Monte Carlo simulations. Okay, last one, which is also an interesting one, heuristic. Okay, so this is a very old concept. And yes, it comes from the Greek, but the main idea here is, there are so many problems in life and in computing and in science that are very, very complicated to find an exact solution. Okay, but that you can think of using a simple rule of thumb that probably gets you, 90% of 99% of the way, or even more. And that's the principle that heuristic algorithms use. Okay, so the idea is that you have a problem which is too complicated, typically to solve exactly, in a reasonable amount of time. And so what's the next best thing that we can do? And usually it's using a rule of thumb as an approach to obtain a good enough solution. And this obviously used, another way of saying the problem is too complex is that the problem search space is too large. And so in those cases, exact methods might become impractical. Now, examples of heuristic approaches are simulated annealing, which simulates the annealing, which is inspired by metallurgy. So it's the idea of simulating the process of annealing in metals to find the optimal solution. Genetic algorithms, which are in reality part of a larger set of family of algorithms in artificial intelligence called evolutionary algorithms that use the laws of evolution to trying to find the optimal solution. And a very, very simple one that we'll look through, which is called the nearest neighbor. And then now I'm going to explain you a bit what the nearest neighbor is about, but in the context of a pragmatic problem, which is an extremely, extremely interesting problem that no one has cracked yet. Again, one of the most important problems in computer science called the traveling salesman problem. It looks like a very simple problem. So we have a list of cities, okay, and distances between each pair of cities. All we need to do is to find the shortest possible path that visits each city and returns to the starting point. Okay? Seems easy, but it's not. How long does this take? How do we find the solution to this problem? List of cities, I don't know, in the US, wherever that you want to visit, and you want to visit all of them, you need to find the shortest path that you visit all the cities and come back to the first one where you started. Yeah?
Well, the brute force one would be intractable.
If you want to, you can do a lower band factorial rapidly with every single possible path. Otherwise, you can do the nearest neighbor algorithm, where you just simply take the closest city from the one you currently are.
Okay, cool. So we are basically what we are going to do. So what your colleague is saying is that if we wanted to find the exact solution to this problem, we need to explore n factorial, okay, possibilities. How big is n factorial? Sorry? It's too big. So if n is very large, to give you an idea, you can use an approximation called the Stirling approximation. And n factorial is approximately the exponential of n. So it's enormous. It's exponential of n, it's intractable. Very, very quickly intractable. So it seems like an innocent problem, but it's one of the big problems in computer science. The reason why it's a big problem is that this is so-called NP-hard, the problem that if you solve it can map to many other problems which would have a huge impact on computer science and on our society. Anyway, so let's look at the simple approach. Let's say this gets really big fast. So we take an heuristic approach here. The heuristic approach is, as your colleague said, start from a random city, and I have a rule of thumb. I don't care what happens. I don't do too complicated things. Every time I am at a city, since I have all the distances, I look at the closest one, and that's where I'm going to go. And then when I am the last, I come back at the first city that I visited. Full stop. Okay? So how do I implement this? That's quite simple. I don't have much time, so I will go just through the code without implementing it. We have a distance between two cities, and the cities here are implemented as tuples. So on a 2D map, just the coordinates, okay? X and Y. So I can compute easily the Euclidean distance between two. That's just a function. It's the distance between the cities. And then what do I do in the nearest neighbor? Well, I have to decide in this list of cities where to start. So I'm going to take a random guess, as I said before, and I start from one of those. I set the start of the tour, so I return the tour as a list of cities that I have visited. That's my solution. So the first one is obviously start, and then I can use a set for the cities, right? Because I want to visit each city only once. Then I remove start because I just visited it. That's where I started. And I set the current city to start. And then I start looping, while there are elements in my set which are unvisited, what I do is to look at the next city, defined as the city, okay, that has the minimum distance with the current city. This here is implemented using the min function with an alternative definition of how we define the minimum using a lambda. So we take the unvisited set, then we have a lambda, and for each city in that set, what we are going to do is to return in the lambda the distance, okay, between the current city and the cities within unvisited. And then we return the city which corresponds to the minimum. Nothing that we haven't done. We append the next city to tour, we remove it from unvisited, we repeat. We set the next city to the current one, and we go on. It's a very simple algorithm. What does it do when you visualize this? It does something like this. So we start from a random city, and then we keep going like that, and in the end, that's the final path. Okay, simple stuff. Now, what about the exact approach? For the exact approach, I have n cities, and I have to do all the permutations in my list of those cities. So if I have, and here the order matters, right? Because depending on the order in which I visit the city, the total travel distance changes. So I have to use permutations, not combinations, because the order matters. Now, for a list of n elements, in a list, there are n factorial possible permutations. And we actually looked at how to get them. So in either tools, you can import permutations, which is going to give you an iterator that gives you one at a time, using next in a loop, the permutation, one permutation for that particular set. And that's actually what we do here. So we have this function with cities. We initialize basically to null or none the best tour. That's what we want to return at the end. We use this interesting thing, which is float inf, which is just a special float that sets the value to a special combination of bits that represents infinity. So for all intents and purposes, that means it's an infinitely large distance to start with. And then once we do that, this has to do because with the fact of how we find the optimal distance in here. So we compare the distance that each time we find to our best distance. And if it is less than that, then for us it's better, right? So we want to start with a very large one. So we run through the loop of permutations using this iterator of cities. For each permutation, we sum the distance between the cities in the permutation, okay? And that sum is going to give us the overall distance, right? Once you've done that, we are left with the last one, which is going back to the first city. And the first city, the distance between the last city, so the one at -1 index of permutation, and the first CD. We add it to the distance. If the distance is less than the best distance, then we set our best tour to that permutation and best distance to that distance. It's quite easy. Well, the issue is this loop. How many permutations are there? Well, there's n factorial. So to give you an idea of what happens when you run instead the other algorithm is that. And we are doing 7 frames per second. Now, that solution is actually different from the one that nearest neighbor found. Okay, excellent. Well, final point here. Obviously, the complexity of near neighbors is order n squared. That's very nice, but it might not find the optimal solution. So whether you can use a heuristic algorithm or not, it depends on your specific problem. The exhaustive search is, we have already covered that case. It's essentially brute force here. And so whether you can afford it or not, it depends on the size of your problem. And with that, I guess here just to summarize the lecture for today, we covered a bit of foundations of algorithms. We have covered what's an algorithm analysis, big O notation, time complexity, and space complexity. And we went through a bit of various families, not all of them, of algorithms and various examples of those algorithms that we have implemented. And with that, we close this lecture. This is my last lecture in the course. On Friday, you will have a lecture which is an advanced lecture with a guest lecturer. And then I believe then from next week, a combination of Shannon and Kat will be lecturing. Thank you. And if you have any questions, I'm happy, of course, to take them as I wrap this up.